Do you know what's cool? Stars. Well, actually, they're not even cool. They're like really hot, like 6,000 degrees hot. That's hot enough for like fusion to happen in the center of them. That's how we make all our heavy metals in the universe. They're creating a yotta energy. Yes, yotta. That's 3 yotta watts. That's 3 with 26 zeros after it of energy. Yeah, they're lit. It's lit. Right, but what happens to a star after they've used up all that fuel that they've been burning up? And how do we classify them? And also, did you know that a lot of what we know about stars today actually comes from a lot of work that women have done in science and have been completely forgotten about? Right, so a lot of what we know about stars comes from the colour that they are, and that's just not in the light spectrum but on the whole electromagnetic spectrum. That tells us about what the star is made of, it tells us how hot the star is, it tells us how powerful it is, and in fact we have a scale called the luminosity scale that tells us just how bright a star actually is. And what we do with all the stars that we know is we put them onto probably the most important graph in all of astrophysics, the Hertzsprung-Russell diagram. The Watty-Wattle diagram? The Hertzsprung-Russell. It kind of came together from 2 men that were working on it at the time, Einar Hertzsprung and Henry Norris Russell. But these 2 men relied heavily on a classification system that was basically made by women in Harvard at the time. That's a really cool story, but I'll get to that later. So this is the Hertzsprung-Russell diagram. It's a way of plotting stars on a scale, so we can actually detect where they go on the scale and how they evolve. So you've got the colour, which is a measure of temperature along the bottom. Remember, the cold is on this side and the hot is on this side, which is kind of the opposite way around that you'd think it would be. And then you've got luminosity, which is a measure of power, or sometimes how big a star is, up the left-hand side. So where do typical stars go on this graph? Well, let's start with your ordinary run-of-the-mill stars, the main sequence stars. These stars are like ultra basic. They're so non-extra, unlit. They fill out a nice wee strip down the middle. Now the hotter, larger stars are in the top left-hand corner, and the smaller, less bright stars are down in the bottom right. Our sun sits just here, right in the middle of average Joe Lane. Hiya sun, thanks for providing us with light and heat. Up in this corner we have the red giants like Betelgeuse. This is the next evolutionary step of main sequence stars. After main sequence stars run out of their fuel, hydrogen, the core collapses because the fusion isn't pushing the core out. This makes the core smaller and hotter, so hot in fact that it starts fusing even heavier elements. The outer shell expands and cools down, making a red giant, which is why they move down to the cooler sides of the graph. This red giant phase is the expected next stage of our own star, and in fact when it does become a red giant, its outer shell will reach beyond Earth. So that's going to happen in like 7 billion years or so don't hold your breath. Smaller stars become red giants and bigger stars become super red giants. And even bigger stars collapse into a massive explosion called a supernova, and they create either neutron stars or black holes. Neutron stars and black holes deserve an entire video on their own, so if you want to see that, give this video a like and leave a comment down below and I'll get that done for you. Right, so back to red giants. What happens to them when they run out of fuel for fusion? Well, the core collapses and heats up again, shedding out all those outer layers. And what you're left with is a hot, small white dwarf. So why do we even plot things on a graph like this? Well, stars that are bigger, so at the top end of the scale, tend to burn much faster than stars at the lower end of the scale. So plotting something on a graph like this helps us tell how old the star is, and if there's a group of them like in a galaxy or a cluster, it can help us tell how old that entire galaxy is. So this diagram, this graph, is absolutely fundamental in determining the formation of galaxies, how far away things are, how big things are. You know, sometimes we have that problem of, is that star really big and far away, or is it just a small star and close up?
Okay, one last time. These are small, but the ones out there are far away.
And by classifying stars and seeing how old the stars right next to it are, we can learn a lot about our universe. Right, so now I have your attention. Do you want to know the real reason why I even decided to make this video in the first place? It's because of the women in science. Pretty much all of the classification of the work leading up to this diagram was done by women. And in fact, one woman in particular, the woman I want to talk about most is the Scottish astronomer called Wilhelmina Fleming, born and raised in Dundee is where she spent most of her days, chilling out Max and teaching in school until her husband thought it would be cool to learn about stars and outer space, and he said, why don't we emigrate to the United States? Right, enough. Basically, Wilhelmina worked as a maid for a Harvard professor at the time, Professor Edward Pickering. Now, he reportedly used to get very frustrated for the men who worked for him, saying things like, my Scottish maid could do better work than you guys. So he hired his Scottish maid. Wilhelmina was hired to be a computer. Now, that wasn't just her sitting around going beep boop, beep boop, beep boop. Computers in those days were the people that did the computing. Wilhelmina spent her time analysing spectral graphs of hundreds of stars, classifying them by how much abundance they had of each element. This work, along with a lot of work from other computers such as Anna Cannon, was the basis of the Harvard classification system, which is still used in astronomy today. And it's this classification system which is quite often on the x-axis of the Hertzsprung-Russell diagram. So it's like really important stuff. Yet it's Hertzsprung and Russell's name on all this sort of stuff, and it's the Harvard classification system. Where is the recognition of the women in this? So anyway, I want to share more stories about really important women in science. So my question for you is, who is your favourite scientist? It can be man or woman. Tell me a little bit about them and why they're your favourite scientist. And do you know of any women in particular that have been overlooked by the history books? Let me know and I might make a video on it, because this topic is like really interesting to me. Anyway, I hope you enjoyed this episode of Science with Steph. If you want to learn more about the overlooked women in science, then you can watch my last video by clicking here, or you can watch the video that the YouTube algorithm thinks you'll enjoy best by clicking here. Alright, I'll see you next week. Bye! How are you going to be able to tell the difference between it if I don't have this on my head?